In this session, we will be discussing about the module 1, and here in this session, we will be discussing about the electrochemistry and energy storage systems, introduction and derivation of the Nernst equation. First, let us see some of the thermodynamic functions. Thermodynamic is a branch of physical chemistry which quantitative relationship between the heat and mechanical energies. What is energy? Energy is a quantitative property that must be transferred to an object in order to perform work or to heat the object. Energy is a conserved quantity. And Helmholtz free energy. What is this Helmholtz free energy? It is a thermodynamic function defined to measure the useful work obtained from a closed system, and it is denoted as A and is defined as A is equal to E minus Ts, where E, T and S are state functions of the system. And coming to the Gibbs free energy, it is thermodynamic function which is related to enthalpy and entropy as G is equal to H minus Ts, and entropy is a quantity that whether a chemical reaction or a physical change can occur spontaneously in an isolated system or not. Change in entropy from one state to other is denoted by S is equal to S final minus S initial. This is some of the basic thermodynamic functions which you have already learnt in a PU classes. Okay, now in this class, next topic is let us see the derivation of the Nernst equation. This question will be asked for 7 marks in our exams. It is very simple and easy to understand. Okay, the Nernst equation which relates between the electrode potential and concentration of the species, which was derived by a well-known scientist called as Nernst, and that equation was then called as a Nernst equation, and it is derived by using a well-known thermodynamic considerations. To derive the Nernst equation, first of all, we should consider a reduction reaction. Okay, consider a general reduction reaction. Mn plus N electrons gives M. Okay, and whenever a reaction starts, there will be a decrease in the free energy, right? That decrease in the free energy by Van Hoff reaction is given by delta G is equal to delta G naught plus RT ln K. And what is delta G? Delta G is a Gibbs free energy. Delta G naught is a standard Gibbs free energy. And R is a gas constant, T is a temperature, and K is a equilibrium constant. Okay, let us see what is this delta G now. Delta G is equal to the maximum amount of work done. Okay, what is maximum amount of work done? It is equal to the number of electrons, Faraday's constant, and the potential. See here, the decrease in the free energy represents the maximum work done, that is minus delta G is equal to W max. Okay, and what is W max? It is a total number of electrons flowing from anode to cathode and the total amount of energy available per coulomb. That can be written as W max is equal to NFE. So that it will become delta G is equal to minus NFE. Okay, that is because minus delta G is equal to NFE, or we can write it as delta G is equal to minus NFE. Okay, so in the same way, delta G naught is equal to minus NFE naught, and the equilibrium constant, it is given by concentration of products by concentration of reactants. For the reduction reaction, we will be getting a M by Mn plus. Now we have to substitute all these values in equation 1. That is like we have considered the Van Hoff equation. There if we substitute all these values, what do we get? We get minus NFE is equal to minus NFE naught plus RT ln M by Mn plus. Okay, and we know very well the Nernst equation gives the relationship between potential and the concentration of the species. We don't want the NF terms here. So divide the whole equation by minus NF, we get. What do we get? E is equal to E naught minus RT by NF ln M by Mn plus. Okay, we want to take the term Mn plus to the numerator, so we can write it as E is equal to E naught plus. Okay, this step is very important. E is equal to E naught plus RT by NF ln Mn plus by M. Okay, what is the next step? Here, next step is we have to convert the ln to log. Then we will get, when we convert from ln to log, we have to multiply by 2.303. Therefore, the equation will become E is equal to E naught plus 2.303 RT by NF log of Mn plus by M. Okay, this is the term we get. And you know, when the concentration of the M is at unity, then we will get, what do we get? E is equal to E naught plus 2.303 RT by NF log of Mn plus. Okay, this equation, no, it will be used to calculate the potential, you know, where we have to use this. Okay, when the temperature is given other than normal temperatures, other than room temperature, the temperature is something else different is given, that time we should use this formula. E is equal to E naught plus 2.303 RT by NF log Mn plus. At normal conditions, normal room temperature is 25. Otherwise, if it is given anything other than that, you have to use this formula. And you know, at 298 K, when we substitute the values of R, that's a gas constant 8.314 and Faraday's constant 96,500, then we get a final form of the Nernst equation, that is E is equal to E naught plus 0.0591 by N into log of Nn plus. This is our required Nernst equation, which relates, you can see here, E is the potential E. Okay, it relates the potential E with the concentration of the metal ions, that is Mn plus. Clear, no? Okay, so for deriving the Nernst equation, first you should write the reduction reaction. Mn plus an electrons gives a M. Then you have to write a Van Hoff's equation. Delta G is equal to delta G naught plus RT ln K. You have to name each and every terms. Delta G is a Gibbs free energy. Delta G naught is a standard Gibbs free energy. R is a gas constant. T is a temperature and K is a equilibrium constant. You have to derive the values for all these things. That is delta G is equal to maximum moment of work done, which is equal to NFE. So delta G will become equal to minus NFE. Delta G naught is equal to minus NF. E naught, equilibrium constant, will become a M by Mn plus. Okay, when we substitute all these values in the given Van Hoff's equation, you will be getting a minus NFE is equal to minus NFE naught plus RT ln M by Mn plus. Okay, we have to divide the whole equation by minus NF, because we are showing the relationship between the potential and concentration of the species. We will get the next term, E is equal to E naught minus RT by NF ln M by Mn plus. Okay, R we can write as E is equal to E naught plus RT by NF ln Mn plus by M. The next step is we have to convert from ln to log. We have to multiply by 2.303. Okay, so we will get E is equal to E naught plus 2.303 RT by NF log Mn plus by M. Okay, this equation used, okay, when temperature is anything other than room temperature, anything other than 298 K is given. Okay, it is easy to remember. Anything other than 298 is given, then you have to calculate this, use this formula for calculating the, you know, in problems particularly. Fine. So when the concentration of the M, okay, when the concentration of M is at unity, we will be getting a E is equal to E naught plus 2.303 RT by NF log Mn plus. Okay, and at 298 K, when we substitute the values of the gas constant 8.314, Faraday's constant 96,500, we get the required Nernst equation for single electrode potential, that is E is equal to E naught plus 0.0591 by N into log of Mn plus. Okay, we will be meeting with the new topics shortly. Thank you.